All right, first of all, I'd like to thank the organizing committee for inviting me to come and share some of the progress we've made. So today I will discuss not just work from my group, but from a collaboration we had. That collaboration was supported by DARPA for the last 3 or 4 years. And the goal of our project was to really try to make a serious effort at demonstrating quantum repeaters using trapped ions. And obviously, it turns out to be a lot more difficult than we had thought, but I would like to share with you some of the progress we've made and convince you how close we are if we were to make a serious run at it. So here, the work I'll present includes a collaboration with Chris Monroe at University of Maryland, Jiang and Lütkenhaus at Yale and Waterloo. They are our theory collaborators. Marty Fayer at Stanford, who has been working on wavelength conversion devices, and Peter Mounds at Sandia National Labs, who's been collaborating with Chris and my team on the trapped ion technology. And a bulk of the work presented here is supported by DARPA, although I'll also include a lot of the work, the background work that's being funded by many other agencies over the years. So I'll start with a brief introduction on some practical framework of quantum networking and basically a brief description of how quantum repeaters can potentially be classified. And then I'll tell you about the current state-of-the-art in trapped ion quantum networking or quantum computing technology, basically. And then I'll tell you about demonstration effort towards the repeater node, where we have done some concrete design of the experiment and also some analysis about how they should perform. And then I'll conclude. So to give you, to make a somewhat meaningful analogy, if you look at the classical communication networks, of course, the first telephone call was demonstrated almost 140 years ago. And then with the invention of these vacuum tubes, the first triode invented in 1907 at Bell Laboratories in Manhattan, they were able to really extend the reach of these phone conversations. And the first coast-to-coast telephone call was made in 1915. Over 4,750 miles, 4,750 miles of distance. And then, of course, after that demonstration, a huge commercial operation of these telephone networks were built. And of course, the technology for building these very conventional manual switching to modern telephone networks that have high capacity optical transmission and very significantly large switches really took on until the early 90s. So basically, from the first phone call to the predominance of telephone networks in the 1980s, over the 100 years, there was only one dominant application of communication networks, and that was voice. Okay. Of course, there were telegrams and things like that, which was a very, very small fraction of the application space. But predominantly over the first 100 years of telecommunications technology, it was all voice applications, pretty much. But we know what happened since the 90s over the last 20 or 25 years. And today we have this internet network infrastructure. And over the last maybe 20 years, the telecommunication industry went through a huge revolution where today all applications are completely dominated by data. And the type of things we do over these networks have really gone from one application to infinite number of applications, like all the cell phones, all the searching that we do. What I would like to make a quick analogy to is so far, when we think about the quantum communication networks, I think the first application we all think about is this key distribution application. But I would like to make a very loose analogy that QKD is really like a voice application. If we build the first quantum network, we'll definitely be focused on that type of applications. But just like data networks, if we can build a very generic quantum network, then there could be a whole host of other applications we can deploy. And that, of course, requires a different class of network capabilities. So there is one of our team members, Timer Islam, will present a poster on some of the work we do on a more conventional QKD. But in this talk, I would really like to focus on some of the key attributes of much more generic, potentially generic and more powerful quantum networks. So what is the essence of communication between machines? So if the voice is mostly communicating between people, data is really communicating between machines. So if you're thinking about generic quantum network, you will have a whole bunch of qubits here and a whole bunch of qubits here, and typically they are stored in some memory, so we could actually use them. And then we have to create some kind of quantum correlation or entanglement across these things, and that becomes a resource over which you can deploy all kinds of different services. The distance of this can be very short. In some cases, you may want to connect different parts of your quantum computers in a local environment. We actually do that, right? When we run a data center, there are small computers that are connected over very short distances, and that still is a communication network. And also, of course, it goes to many tens of thousands of kilometers, reaching the other side of the globe. And the type of applications, if you're concerned about QKD, then the nice thing is these quantum resources on either end immediately collapses to classical bits, right? You basically measure them and use classical bits. And therefore, you don't really have to worry about building exotic quantum memories or quantum computers on either side of the node. But if you are interested in either long-distance communications or very generic quantum interconnects for shipping quantum data across, then in general, you actually have to have a much more sophisticated quantum devices on either side, either end of this communication link. And of course, when you think about networks, we're not only talking about point-to-point communications, but there can be many nodes along which quantum resources are being shared. Now, if you actually have a very generic quantum network like this, then this could actually be opened up for all kinds of applications like distributed quantum computing and all these other protocols that we have discussed throughout the conference this week. So how do we get there based on some of the capabilities that we have today? I'd like to think about a very simple framework, which is experimentally advanced in the sense that we could actually do this routinely in many laboratories today. And here, basically, you have a quantum memory here on one end in two different places. This could be separated by a short distance or a long distance. But what we do is we excite this quantum memory in such a way that it emits a photon. Okay, so this will have to be a particular type of quantum memory where you can generate a photon. But we do this in a way that this quantum memory and the photon it emits is actually entangled in some degree of freedom. Okay, so you create an entangled pair of a memory and a photon. Now, this kind of experiments have been done over the last 10 years or so. Between the first experiment was demonstrated between ion and a photon, but between atom, NV centers, and quantum dots have been entangled with photons. But the interesting trick is you do the same thing on the other side and make sure that these two qubits are so similar that the two photons that are emitted are actually indistinguishable. Then what you can do is you can let these two photons propagate and let this interfere on the beam splitter, and then you look at it with the detector, and this beam splitter and the detector basically performs a Bell state measurement. And when that happens, basically you can teleport the state of one of the particles, C, into the state of B. Basically, B and D is your entangled pair, a Bell state. And then you take your C, which is input state, and then you do a Bell state measurement between C and D, and along with that, you can teleport this C into B. And because initially A and C were entangled, once you do this teleportation, now this memory A and memory B are entangled. Okay? And this is called entanglement swapping, because you start from two entangled pairs, and then you interact the photons, and then you end up with the two particles that are entangled that have actually not directly interacted. So this is a very specific implementation of entanglement swapping, but the nice thing about that is the mediators are photons, which are very easy to propagate and manipulate, and then the resulting entangled pair are actually stored in a very stable and nice memories. Okay? So with a good quantum memory, the generated entanglement can be stored and used for deterministic quantum logic operations. And this actually opens up opportunities for utilizing state-of-the-art photonics technology in fibers, in telecom technologies, or integrated photonic integrated circuits, all kinds of technologies that are available to us today. And of course, using this very simple protocol, we could actually build a quantum repeater now. So here now you think about this atom here, this memory here, and that memory here, emitting a photon through a long optical fiber. When the Bell state measurement is carried out, you can create an entanglement here. But in the meantime, you also generate entanglement here in parallel. And then whenever the entanglement generation is successful, you store that pair until all the links have entangled pairs that are generated. And now you can do a Bell state measurement between these two memories, send a classical bit of information, and now you can create an entanglement between this memory here and this memory here. And now the distance over which the entanglement is distributed has just doubled. And we could actually cascade this process in a nested format. Every time you do an entanglement swapping at the memory level, doubling the distance, and then you can very readily distribute entanglement over almost arbitrary distances. So that's how a quantum repeater works. Now, in many practical cases, these memory particles that we use to store qubits in the local node may not emit a photon that is very favorable to long-distance transmission. And in those cases, we could use nonlinear optics techniques to take these photons, either visible or UV photons, with some nonlinear quantum wavelength converters, to make sure that this qubit, a photon that's carrying the information, is now converted to a more transportation-friendly wavelength, so that they can be transmitted for a very long time, long distances. And once these basic elements are there, you can imagine going in this. This is an example of an ion trap version of this technology. You can imagine building much more complicated structures to allow multiplexing and so on, to improve the performance of the basic quantum repeater operation. Now, dealing with, but in reality, because the communication channel is by definition lossy, you actually have to worry about photon loss errors. There are two errors. Once you emit a photon, in many cases, these photons actually get lost. They don't reach the destination. And also, when you're doing these entanglement swapping operations at the middle of the node, these operations are not necessarily perfect. They're not 100% fidelity, and therefore you will incur some errors. And every time a photon is lost or errors occur in your local operations, you will actually have some error that's created in that process. So there are ways that we can cope with these errors. One, there are ways we can cope with these errors. In this loss error situation, what you do is once you first of all pick up a protocol where if the photons actually don't successfully arrive, you naturally discard that process and start over. Okay, so this actually only succeeds probabilistically. It is not a deterministic process to generate this entanglement. But again, the fact that you store the generated entangled pairs in memories allow you to store them and use it in a deterministic manner once the process is successful. And that's because if you design the protocol carefully, this process can be heralded, meaning when it succeeds, then you know. And that classical information of a successful event can propagate and allow you to store that information carefully. So that is a heralding process. You need a two-way communication to be able to do that. But if you do that carefully, these photon loss errors can be coped with. Now, there are even more advanced ways to deal with it. You can actually now, instead of sending individual qubits, you can send the qubits encoded in some kind of a quantum error correcting code. In that case, the deletion of a qubit will result in some error. But if your code is big enough, then your code can actually make up for that error by the nature of the error correcting process. In this case, you can actually do a deterministic one-way communication in such a way that you send your data one way, and the decoder can actually tell when the photon loss has happened, and then basically fix that process. Now, the operation errors, which means when you're trying to create this Bell pair and do local operations, Sometimes those fail, and the way you do that is you can actually now create higher fidelity entangled pairs from multiple entangled pairs, and that is again called an heralding process. You know when you succeed, and that does actually require two-way communications. But the local operation error can also be corrected by utilizing quantum error correction. And based on how we cope with both loss errors and operation errors, my colleague Jiang and Lütkenhaus have classified these quantum repeaters into 3 different generations. So in first generation repeaters, both loss errors and operation errors are actually handled by the heralding process. And here you can, in principle, overcome the losses and errors, but it actually does require a lot of resources. It is a very slow protocol. In the second generation quantum repeaters, these quantum error correction, the local errors are controlled by quantum error correction, which is a lot easier to do than handling loss errors. So we actually do a heralded communication to cope with the loss errors, but utilize quantum error correction to deal with quantum operational errors. And the third generation quantum repeaters actually uses quantum error correction on both of these. Now these can in principle give you extremely fast quantum protocols because there is absolutely no two-way communications that's involved. But the downside is the experimental or the technological demand to implement these are really very severe. For various reasons, to try to do anything really practical in the laboratory, we are somewhat confined to working with first generation repeaters. All right, so let me now move on to trapped ion technology for quantum networking. What is available today in quantum technologies in trapped ions? First of all, I'd like to highlight some of the advantages of trapped ion systems, especially in the operation for candidate for operating quantum repeaters. It is one of the best qubits, and high fidelity operation is available. So coherence times somewhere between 1 to 1,000 seconds have been demonstrated in hyperfine qubits. State preparation and measurement errors, which is sometimes called spam errors, are typically in the 10 to the minus 3 to 10 to the minus 4 range, and we think that in the very near future we could probably reach 10 to the minus 5 range. Single qubit gate errors are currently, again, just within the last couple of years, in the 10 to the minus 4 to 10 to the minus 6 range. And then the 2 qubit gate errors are in the 10 to the minus 3 range, and we believe that pushing this further down is also possible. And there are many publications over the course of the last 20 years that shows you how things can work extremely well in the modern day ion trap systems. But I think what is really exciting is just over the course of the past 5 years or so, maybe 5 to 10 years, people have been introducing new technologies to not only make the ion trap performance go higher, but also allow them to have much better optical interfaces relevant for quantum repeaters. So one example is these microfabricated ion traps. Now these are microfabrication. These are ion traps that are fabricated by using more conventional silicon fabrication techniques. And today, if you want the specific ion trap, you tell them what you want, and your partners at the foundry will design and fabricate them on a silicon chip. They'll package it just like any other IC would arrive in your office. And then we can put it into our lab, and we can actually do operations like this. And here, what you see is my colleague Jason Amini is trapping individual atoms here, and once the atom is trapped, he would actually move it over here and deterministically build up a chain of ions, which could be used as a quantum register. Some of the more advanced traps, once you have these traps, we need to bring in some laser beams to manipulate these qubits. And some of this actually represents one of the state-of-the-art ion traps that we make at Sandia National Labs. HOA stands for high optical access. It allows you to bring in all kinds of laser beams that's needed to manipulate these ions without unwanted interactions or scattering events. Now, using some of these advanced technologies, now this specific experiment doesn't quite utilize those chip traps yet, but my colleague Chris Monroe at University of Maryland, we actually can create a very generic full-blown quantum computer today. So this actually is a fully programmable 5-qubit quantum computer. Okay, and this is made up of these 5 ions that we have here. Now these are specific optical devices. We actually manipulate these qubits by bringing a pair of laser beams, counter-propagating from one side and the other. So this is one beam that's globally addressing all of the ions here, and a bunch of laser beams that are generated, individual laser beams. And what he can do is he can turn on one of these laser beams at a time. Each laser beam focus onto individual atoms, and here we show operation of 10 such channels of these optical switches. So we can actually turn on and off each individual laser beam hitting one of each ions, right? And what that allows us to do is do an individually addressed quantum logic gate on a 5-ion quantum system, trapped ion system. And here it shows that we could actually also measure the state of all these 5 individual ions independently. Right now there is a little bit of crosstalk, so the operation is not perfectly ideal, but we can nevertheless do a very, very good job. And this actually gives you a 5-qubit system with a full-blown connectivity. What this means is although the ions are arranged in a straight line, you can actually pick arbitrary pair of ions and operate 2-qubit gates on them. Okay? And there are 10 of them. 5 choose 2 is 10. And this shows the characterization of all 10 2-qubit gates CNOT gates you can operate on those ion trap. And this is, for example, CNOT between ion 1 and 2, CNOT between ion 2 and 4. You can do one between, say, 1 and 5, and so on and so forth. And you can see that the fidelities of all these operations are on the order of 95 to 99%, somewhere in between. And having this kind of a very flexible configuration, you can now operate arbitrary algorithms on them. So they demonstrated running several algorithms, for example, on exactly the same hardware. This is an example of running Deutsch-Josse algorithm that is made up of a whole bunch of state preparations and some CNOT gates and a bunch of measurements. You can actually pick whatever function you want that will have a different configuration of CNOT gates you have to do. But because our system is fully programmable, you can actually do that and get whatever result you want. You can use exactly the same machine to operate a 5-qubit quantum Fourier transform, which again requires all kinds of CNOT and controlled actually rotation gates that are described here, and we can actually do a fairly reliable phase estimation algorithms and so on. So the whole point here is a small-scale quantum computer capable of fully programmable algorithm execution exists today in trapped ions. Okay? And they will only get better over time. So you can actually potentially deploy a full-blown quantum computer as a repeater node if you choose to do that. Okay? Now let's talk about the optical interfaces. The optical interfaces are built this way. We have 2 ions. We come and excite them with short pulse lasers. And these 2 photons come. You can interfere them at a beam splitter and make a measurement. Now, because of the so-called Hongou-Mandel effect, these 2 photons will never go out in the 2 opposite directions if they're exactly the same. So if you actually detect 2 photons at both detectors simultaneously, that basically means, say, the polarization of one and the other photon that are detected has to be different. But there is an HV, but there's also a VH scenarios where these 2 detectors can click at the same time. And because these HV and VH are not distinguishable because of the beam splitter, when both detectors go off, it actually signals the fact that your photon states were in this Bell state. So you can actually identify that Bell state with a success probability of 1/4. And the generation of entanglement over here is now the rate at which you can generate that is determined by 1/4 times R, where R is the repetition rate of the experiment. And then the quantum efficiency of the detector, the collection efficiency of the solid angle over which you're collecting the light, and the probability that it will get into a single mode fiber. And all of that needs to be squared. And because all of these are not very large numbers, at the end of the day, our entanglement generation rate traditionally has been extremely slow. So in some of these first demonstrations on any physical systems that's been demonstrated so far, the entanglement generation rates, remote entanglement generation rates by photon entanglement is about somewhere between maybe 1/30th to 1,000th of a hertz, meaning you will have to wait about 30 to 1,000 seconds before you see a single event. And although the ions are extremely good memories, the ion memory coherence time is typically on the order of a second or so. And therefore, this ratio between the entanglement generation time to decoherence time tend to be very bad. Meaning, if you want to build a repeater, you want to create this entanglement. By the time you create an entanglement and wait for the next entanglement to be generated, your qubits will die. Right? So they're actually not very useful for building larger devices. In order to really improve this, you actually have to shrink this ratio in such a way that this entanglement generation time is very short compared to the coherence time of the quantum memory. Okay? And that requirement is extremely challenging to do. This was actually the state of the art in probably 2010 or so, and we started looking at this problem to try to see how far we can improve this performance. And then we realized that, first of all, you can actually, instead of using 2 detectors, we can actually use 4 detectors. And if you do that, then you can distinguish 2 out of 4 Bell states, and therefore the success probability goes up by a factor of 2. Okay, this 1/4 is replaced by 1/2. But that's a significant win, but not big enough to be useful. So we actually looked at this problem very carefully and came up with a strategy over which you can actually collect a much bigger fraction of the light. And we went and fabricated this lens that has a numerical aperture of 0.6. And what that means is now collection angle is about 10%. We have a detector efficiency, and the coupling efficiency was still pretty low, but we made enough progress on the order of a factor of 100 improvement or so that now our entanglement generation rate, we can generate about 5 to 10 events per second. Okay, so now if you look at this ratio, our ratio of entanglement generation time is actually a lot faster than the coherence time of the detector. Okay? So this is the first time that this metric has been exceeded in any physical system, but we need to push this up much further along before you can think about building quantum networks out of them. These are the similar numbers that I quoted. It turns out that aligning this high numerical aperture lens to the ion is a little tricky. So if you just put it and roughly align it, you can see that the ion image is very bad, meaning there are lots and lots of aberrations. We could actually put a lot of effort in making sure that this alignment of this lens to the ion is very carefully done. And then with that, we can improve the coupling efficiency from about 40% to maybe 50% or so. And in the meantime, we also collaborated with JPL and NIST to try to fabricate the single superconducting nanowire single photon detectors that are more adequately operational in the wavelengths of interest for our systems. And now we actually have devices that have about 70 to 80% detection efficiency. And using these 2 advancements, although we haven't quite done it yet, with these 2 advances that we have made since about a year and over the last 2 years or so, we feel that we could probably generate an entangled pair every 5 to 6 milliseconds. Right? It means hundreds of events per second. And if we can actually push the limits of performance of the components that we have, we can really get it down to about a millisecond time scales. In order to go even further, we have an effort trying to build a cavity QED system where using the cavity QED effect with these kinds of parameters that are currently anticipated, you can eventually collect over 70% of the individual photons emitted by ion into a single mode fiber. Now, when you do all of that, you can push the generation time of these entangled pairs to be short enough so that they're comparable to the local 2-qubit gate time. And at that point, I think we could actually do a very interesting set of experiments, including a realization of quantum repeaters. Another element is this wavelength converters. This is a collaboration with, this was actually work done by Marty Fayer's group. One of the ion species that we're looking at emits a photon at 650 nanometers, and we have to convert this 650 nanometer photon to a telecom photon at 1595 in this example. And what they have done is and in order to make sure that this conversion is done with very low background photon count, dark counts, we actually have to use a two-stage conversion process. So they devised these integrated devices where two-stage conversion with a U-band that dumps all unwanted pump light and the spurious noise photons that are generated is filtered out. And they can actually demonstrate that both stages of this wavelength conversion succeeds with a probability of over 99%. This conversion efficiency can be extremely high, at least inside the device. And the coupling in and out of the device, they could actually do that with somewhere between 80 to 90% efficiency. So taking a 650 nanometer photon generated by an ion, and converting it to 1595, which is a telecom band that can propagate a long distance, is the technology have actually been successfully developed for that. Now, I think this is the last section. Again, I think I have very short time, so I'll try to run over this fairly quickly. This is actually an idea that I collaborated with Jiang and Noble Lütkenhaus to come up with. So the question is, given all of these technologies that we have at our hand today, can we actually come up with a demonstration of a repeater-like operation where we could do better than a direct transmission of photons in a typical standard QKD system? Okay, so we start with the Eckert protocol. This is so-called the measurement device independence QKD protocol, where we start with a bell pair. And then we make a measurement on either the Z or the X basis, and then you can actually come up with the pairs of zeros and ones, and that could be used to distill key, and that's the standard Eckert protocol. But we could also generate this qubit entangled pair between the particles, say 1 and 4, photon 1 and 4, by injecting another entangled pair. Now this, if you have two qubits prepared in zero state here, and if you do a C0 and do a C0, Hadamard and a C0, which Hadamard here is actually now included in one of these measurement basis rotations, then this is actually a fully entangled pair. And with this entangled pair, I can actually make a measurement and then rotate. And if these two were initially entangled and those two were initially entangled, this just describes the Bell state measurement that teleports this quantum state to over here, right? So this actually allows you to create a secret key between these two qubits by starting from two pairs of entangled particles. And of course, exactly the same thing happens in the sense that this qubit can also be looked at plus and minus bases, and therefore it's a fully entangled pair from which you can distill a secret key. So the question is, can we actually do this experiment with the experimental capability that we have today? And this could potentially extend the reach of the system by a factor of 2 in the best case. So here now I'm thinking about this initial pair as a quantum memory spitting out a photon. Remember, we could do that, ion-photon entanglement. And over here, I have another ion-photon entanglement, and this photon is sent towards Alice, and this memory spits out and sends a photon towards Alice. This one sends a photon towards Bob. And then once the photons are sent, then we could actually do a Bell state measurement between these two memories by doing a C0 gate between them and doing a measurement. And based on this measurement basis, we could actually go over here and change the state of this photon. And now this photon and that photon is entangled, and then now I can make a measurement, and I can actually extract a set of keys, right? So I've actually just taken this circuit and replaced them with a memory photon entanglement, a pair of them. Now this is nice, but this is a problem because the Bell state measurement requires C0, which takes a long time, and the measurement, which also takes a long time, and the classical bits also have to propagate. And all this time, these two photons have to be stored for a very long time, which is somewhat unrealistic. You have to store photons for milliseconds if you want to do this protocol. But what we noticed two things. First of all, if you look at Alice's photon, once the photon is emitted and arrives at Alice, Alice doesn't have to wait. She can just make a measurement because she doesn't have to do anything to the photon, right? So I could actually move this Alice's measurement right away. So this quantum memory sends a photon to Alice, and Alice just measures it. And then she picks a basis, whatever basis she wants, and then she measures it, okay? And then on this side, it looks like we actually have to, and let's take the case where we're doing a Z measurement in Bob. it looks like Bob will have to wait until all of these things are done and the classical bit is received before Bob can actually make a measurement. But first of all, we noticed that if you do a X measurement based on this, you do a Z rotation on this. But if your measurement is done in Z basis, this Z rotation doesn't do anything. So you actually don't have to do that at all. Okay? And then, he only has to wait for this result and decide whether he wants to do an X basis or not. But if you do a X rotation and make a Z measurement, then you get a 0 or 1, right? You could also revert the order and actually make a photon measurement first, and then if the repeater tells you that you had to do an X operation, then you actually make a measurement and you basically flip the classical data that you have before you generate the key. So what this tells you is, you can actually do an experiment where an ion emits a photon, and Alice immediately measures that. This ion emits a photon and goes to Bob, and Bob immediately measures that too. So they don't have to wait at all. And then once Alice and Bob says, okay, I've measured my qubit, then that means both photon emission and detection has been successful. Then you actually go do this Bell state measurement between the qubits, and then send that information to Bob. And then Bob can actually decide to whether flip his bit or not, and then you can actually generate a secure qubit. So this actually now puts an experimental configuration that is totally doable. Okay? All right. So this basically shows how we are actually going to do it, and I think but the real interesting question is, if we can actually do this experiment, can we actually show advantage over a standard QKD protocol? And that analysis was done by David Luong and Norbert's group. And here we show the distance versus rate curve for both the TGW bound and the plot bound we heard about yesterday. And we also compare that to ideal BB84 using true single photon sources. And we also have single photon BB84 with realistic detectors. And this number 5 is kind of the realistic decoy state QKD using conventional detectors and so on. And when we look at put in all the parameters of our experimental capabilities that are feasible today, I think we have, and this actually is the rate versus distance curve. Initially, because we have 2 photons being sent in the opposite directions, the rate actually decays as 1 over the attenuation length with a half exponent. Whereas if you just do a simple QKD, it actually decays a little bit faster. So there is a little bit of a blip here over which we can actually do better than a direct transmission compared to, say, a decoy state BB84. Okay? So this analysis also shows that in the space of coherence time and the overall coupling efficiency, overall efficiency of the protocol, in this curve, if you're really up here, way up here, then you can actually beat even the TWG or TGW or the plot bound as well. Okay? But all of that means your total overall efficiency, which is capped by 2/3 by the state preparation due to the atomic structure. If you can, and then you have to make sure that your coupling efficiency, your wavelength conversion efficiency, and your detector efficiency all have to be pushed very close to 1. Okay? But I think we've shown you that with the cavity QED, with the wavelength conversion devices that we have, we believe that we can push this number very close to maybe 50% or so, in which case we'll have a shot at really beating all kinds of theoretical bounds, even with this very simple experiment. All right, so as a conclusion, hopefully I've convinced you that the trapped ion platform provides like good memories and even a full-blown quantum computer today that could potentially be deployed here. The demonstration of a useful quantum repeater which beats the standard QKD protocol remains a very big challenge, but it looks like those are kind of within reach. We have to work on improving overall system efficiencies, but the necessary technologies are all under development, and then the system integration will require substantial and non-trivial effort. I'd like to thank all my collaborators and support from the funding agencies that allowed us to do this work. Thank you.
I think we only have time for one quick question.
When you generate the ions, there must be some polarization issue. ESM measurement to align the polarizations together.
Yes.
How
Yeah, so I mean, you can use polarization or you can use frequency, you can use different kind of degrees of freedom. And each will have its own challenges, but you have to make sure that, but you have to collect it in a way that the two polarizations that we collect are orthogonal. And in this protocol, we will use a circularly polarized light of both directions. And then when you build a Bell state detector, you have to make sure that the polarizations are aligned. But those are, I mean, things that you can do. Not trivial, but doable.
All right. Thanks, speaker
Thank you.
again.